Let A be an n by n real valued square matrix of rank 2 with sigma I equal to 1 to n, sigma j equal to 1 to n, A of ij square equals 50. Consider the following statements. One eigenvalue must be in closed interval minus 5, 5. 2. The eigenvalue with the largest magnitude must be strictly greater than 5. Which of the above statements about eigenvalues of A is necessarily correct? So this is a question regarding eigenvalues coming from linear algebra. Now in this question, after we solve it, we will see that statement 1 is correct and statement 2 is false. Proving that statement 2 is false is very easy, but proving that statement 1 is correct is a lengthy process, and there are multiple theorems which we need to know from linear algebra in order to answer this question. So this is a difficult question here. We will try to see how we can prove statement 1. So in statement 1, it's given that it's an n by n matrix. So let the eigenvalues be e1, e2, etc. up to en. Now it's given that the rank of matrix is 2, which means that n minus 2 eigenvalues must be 0. There will be only 2 eigenvalues which may be non-zero, e1, e2. The rest of the eigenvalues of this matrix must be 0. Which are theorems you need to know in order to answer this question, I have underlined in red color. So you need to know this first. Now it's given that the matrix is symmetric. Okay. It's given that the matrix is symmetric, which implies that A is A transpose. So A into A transpose equals A into A, since A is symmetric, which equals A square. So for this matrix A square, the eigenvalues are e1 square, e2 square, and the rest would be 0. How we got this is, for a matrix A, if the eigenvalues are e1, e2, etc., then for the matrix A square, the eigenvalues would be the square of whatever were the eigenvalues of the original matrix A, meaning the eigenvalues would be e1 square, e2 square, etc. up to 0. This also is a theorem which you need to know. Now the sum of the eigenvalues here would be e1 square plus e2 square. Let's name this statement 1. We'll come back to this later. Now consider a matrix of the form A, B, C, etc., D, E, F, G, H, I, etc. Let this be an n by n matrix. When we multiply this matrix with the transpose of this matrix, transpose of this matrix is A, D, G, etc., B, E, H in the row, C, F, I, etc. to both sides. So when you multiply these two matrices, you will see that, let's multiply the first row with the first column. It would be A into A square plus B square plus C square, etc. throughout this row. That would be the first value here. Second and third let's ignore, fourth let's ignore. The second row, second element, that would be D into D plus E into E plus F into F, that is D square plus E square plus F square, etc. like this. Similarly, the diagonal elements here would be the square of each of the elements here. I'll repeat it. When we take a matrix A and multiply it with A transpose, the sum of the diagonal elements of A transpose would be equal to the sum of the squares of each of the elements in A, which I have written as sigma I equal to 1 to n, sigma j equal to 1 to n, A of ij square equal to trace of A into A transpose. A into trace means sum of the diagonal elements. Now A into A transpose is A square, since in the question it's given that the matrix was symmetric. So we can rewrite this as trace of A square. Now trace of a matrix is the sum of the diagonal elements. That will also be equal to the sum of the eigenvalues. So trace of A square we can rewrite as sum of the eigenvalues of A square. Now we'll come back to statement 1. Sum of the eigenvalues of A square was e1 square plus e2 square. So here we have proven that sigma I equal to 1 to n, sigma j equal to 1 to n, A of ij square will be equal to e1 square plus e2 square. Now in the question it was given that sigma I equal to 1 to n, sigma j equal to 1 to n, A of ij square was 50. What that means is that e1 square plus e2 square equal to 50. Now e1 square plus e2 square equal to 50 means that at least one of e1 or e2 must be less than or equal to 5. If both are less than or equal, if both are greater than 5, then the sum of the squares would be greater than 50. So at least one eigenvalue, even if it were eigenvalues of matrix A, so at least one eigenvalue must be in the closed interval -5 plus 5. So thus we have proven that statement 1 is true. So coming to statement 2, the eigenvalue with the largest magnitude must be strictly greater than 5. Now to disprove this, it is pretty easy. Let's take the matrix 5 0 0 5. Now sum of squares of this matrix is 5 into 5 is 25 plus 5 into 5, that is 50, which satisfies this condition. It's an n by n real valued square matrix. Rank is 2, 5 0 and 0 5 are independent vectors. So the rank is 2 here. So this matrix satisfies this condition. If I try to solve for the eigenvalues of this matrix, I will get that 5 minus lambda 0 0, 5 minus lambda, determinant of that would be 0, which means lambda would be 5 comma 5. Now both the eigenvalues are 5 and 5. Now in the statement it's saying that eigenvalue with the largest magnitude must be strictly greater than 5. This is clearly wrong because both the eigenvalues here are less than or equal to 5. So this statement is false. Now we look at the options. Option B, 1 only, is the correct answer.